Welcome everyone. So today's first session is being given by Nico Formánek from the or actually in German, the highest performance compute HLRS in Stuttgart, Germany. You are a philosopher of science, a research scientist at HLRS, and also the department head of the group of philosophy there. And we're very excited for you to tell us about computing power and model selection. Please take it away.
Yeah, thanks, Jonathan, and thanks for the invitation here. I'm very happy to be here. So actually in English we call it high performance computing center, so we don't have this distinction that we are actually the best one in Germany, but we still think we are, right? So I realized that this is like a seminar about the history and philosophy of mathematics. So I just want to make this
and physics
and physics. No, okay. So I'll be talking perhaps more about the physics aspect. But to get it out of the way first, so I'm not using like this computing power concept in any formal way, right? So I won't tell you anything about the computational complexity, polynomial time or whatever. And the model I'm also losing in this very loose way philosophers of science talk about models. So I won't go into much detail about what that means, but it's basically a term that covers structures in science that can be theories, but also can be maybe a little less complete or strict than theories, which are perhaps a bit closer to experimental observations. So it's not a logical model, right? Or a model as we know from model theory in logics. So the motivation for this talk, or for why I was thinking about like these two concepts together, was that many philosophers of science, or also I think many scientists, they worry about this problem of overfitting, right? That if you have data and you want to try to figure out in some way the correct model, and your model is too flexible, well then what are you going to do? And if you throw lots of computing power at that, you will perhaps select the wrong model. So that's a worry that you find very often. In science, most often statisticians talk about it, but I guess nowadays it's also considered in machine learning, right? So basically where you have automatic methods and you try to be like very agnostic and let the data, so to speak, for themselves. And this worry is often illustrated with a peculiar example from the history of science, namely the discovery of the elliptical orbit. Something that was discovered by Kepler. I will talk in some detail about this historical discovery. But just to complete this motivation, so in this computing power and model selection overfitting problem, there are lots of connections to problems philosophers of science, that philosophy of science has talked about and thought about. Underdetermination is one of them. Theory ladenness, of course, the problem of induction, and also like uncertainty, and how you would propagate that through your models and your theories. So I will touch upon all these concepts while discussing this historical example of the discovery of elliptical orbits. Okay, so there's like this textbook version. I'm sure many of you have already encountered. So if you have a training in physics, you will encounter this in physics textbooks, but philosophers of science also use it. I'll give later some, I would say some examples where philosophers have tried to refine that a bit, but it goes a bit like this. So they all start out with noticing, well, Kepler somehow discovered that the orbits of planets, actually one has to say here, it's actually, he only considered one orbit, right? He considered the orbit of Mars, right? So this is the one where he basically discovered that the orbit of Mars was an ellipse. So they noted that, and of course it was some kind of revolution in science that has been discussed a lot. So the story goes like this: they say Kepler, he has this great data, great observations that somebody made, not he himself. And then what he does is he tries to fit this traditional model that came down to him from basically antiquity, called the epicyclical model. Probably you have heard of this too. And then he notes like it doesn't work out very well with his observations, right? Because they were so good, he somehow could reject this model from the observations. And then he somehow comes up with this elliptical function. Yeah, he fits that, and he knows the agreement is excellent, and this is how this elliptical model then gets selected. So this is a very simplified story, normally that's normally told to you in philosophy of science, but also in physics textbooks and in other contexts. Historically, it's not quite accurate, and I will say later more about how this discovery actually happened or what historians of science have found out about it. But this textbook version, I think, can be traced back to John Stuart Mill. So here I have a couple of examples where famous philosophers of science used this discovery of the ellipse as some kind of illustration of their theories, of their philosophical theories. So often they had some kind of idea how science works, and then they say, well, if you look at Kepler and this example, then you will see that my theory is actually correct. And in 1843, John Stuart Mill, he wrote this famous system of logic where he was concerned with induction, inductive reasoning. But interestingly, he used this Kepler example as some example for non-inductive reasoning. So he says Kepler basically didn't do any kind of inductive generalization there. What he did was some kind of, he plotted the data points and then he saw the ellipse emerging from that. So this is what Mill states. And of course, many people coming after Mill, they have noted that Mill probably never read Kepler's book, right? A bit later, Buell wrote some kind of counterpoint to that. Buell himself, a scientist, a physicist, he noted, yeah, this is actually not quite right what Mill says there, and he says, yeah, there's actually some induction involved in Kepler's reasoning. Yeah, he says the observations that Kepler made were actually theory laden, so he had to take an inductive leap to go from these observations to the ellipse. I will talk about this in detail later, what exactly Kepler had to do to his observations, but it was certainly not as easy as Mill thought. Later in the 19th century, Peirce, he also notes that Mill probably didn't really pay attention to what Kepler was doing and was just pushing his own ideas. But in the end, he does the same thing. So he says, well, if you look at Kepler actually is a nice example for abductive reasoning. So abductive reasoning is this mode of inference that Peirce came up with, right? So another philosopher trying to illustrate his own theory of Kepler. And abduction as a mode of inference is basically guessing. It's a bit more than that, but so what Peirce argued is that, well, I mean, Kepler guessed that the orbit would be an ellipse, and in retrospect, after that, he tried to justify it with observations. So this is basically what Peirce wanted to say, and then we make some leap. We skip over lots of philosophers discussing Kepler, and we come to almost contemporary times where people got interested in different aspects of this model selection problem. So I discuss here specifically Paul Humphreys, who wrote a book about the philosophy of computer simulation in 2004. And in this book, he has like a very short chapter where he voices a certain worry about the flexibility of these models, from antiquity to epicyclical models, and the role computing power can play in fitting them. So this I will discuss later too. And well, in 2007, Spanor sees more like a statistician, but he published this in a philosophy of science journal. He published an article where he has like some data from Kepler, and he tries to convince us that if we follow his ideas from statistical model checking, then we could actually see from the statistics that the antique epicyclical model is bad and the ellipse is the better model. So, and I'll talk also about a bit this argument Spanos makes. Anyhow, so this is like a nice story, maybe perhaps also in philosophy of science, where you can see that philosophers, they started like with a very simple impression of how a scientific discovery happened and then refined it a bit over the centuries. Okay, so now, because this is basically the connection to computing power, I will I have here this quote from Humphreys, where he generates this worry about overfitting. So he has this counterfactual situation where he imagines that Kepler, who we know wrestled 10 years with this problem of coming up with the elliptical orbit, he makes this thought experiment that if we would give Kepler a modern computer, then he could have just used this epicyclical model and fit it to the data perfectly. Yeah, no problem. And of course, this has the unwanted consequence that we would have perhaps not found the correct orbit, or at least what we now think is the correct orbit. Or maybe it would have been this.
But that is 2004. Imagine if Kepler had artificial intelligence.
Exactly, yeah. Yeah. So I mean, nowadays, if you give him some NVIDIA GPUs, he could do billions of parameters. But I mean, for the observational data, as we will see later, he wouldn't have needed that, right? So, but yeah. Well, I mean, the problem with computing power, that was already obvious at Kepler's time, right? So Kepler tried very hard with a local mathematician from Tübingen, a neighboring town where we are situated, with our computing center, they tried to come up with a mechanical computer to do exactly such astronomical models. I mean, nothing ever came out of that. I mean, these things, we have a model of that at our computing museum. It's basically a wooden frame where you put some sticks in. So it's yeah, it never really worked. But anyhow, so it's maybe not too far out, this counterfactual. Okay, so just to give you an idea about the people involved here, Kepler is like 17th century, and the model he had, he published first in the Astronomia Nova in 1609. That is the big book basically, and the competing model, if you want to think about this as a model selection problem, the competing model is the epicyclical model, which dates back to at least Ptolemy in the Roman times. So Roman astronomer, and that has been refined through the centuries, of course. So, but basically the idea, as far as we can trace it back, we find it in Ptolemy's Almagest. So there's like more than 1,000 years between these two models. And in the meantime, astronomers, they tried like basically different versions of what Ptolemy had envisioned. I'll just show this to you, a very simple version. So there are 2 points to note. In Ptolemy's model, everything has to be a circle, right? And of course, astronomers noted that it's very hard if you just use circular orbits. Yeah, you cannot fit the observations to circular orbits, so they tried to add smaller circles which would then rotate on the circumference of a bigger circle. These are called the epicycles. And this is why this whole thing is called an epicyclical framework. And it's also often, but not always, done in a geocentric framework. So your observations, because you do them on Earth, this is why they probably wanted to directly fit them in this coordinate system. I mean, nowadays we know that we can transform through all these coordinate systems at our will, but back then I think they really had this preferred coordinate system where they tried to make things fit. Of course, I mean, you had like these 1,000 years of development within this epicyclical model, so they changed this too, right? So you might remember Copernicus. He basically came up with an epicyclical model which was heliocentric. Kepler, though, the model I'm discussing here of his, the elliptical model, is basically heliocentric. So he decided from the outset of his Astronomia Nova that he would work in this heliocentric framework. Yes.
If you transform the heliocentric model to like a geocentric coordinates, how close is the epicycloid model to?
Yeah, that's a question, right? Depends on your epicyclical model. So I'll talk a bit about this later because this is a question that you can have, right? So, and actually this is something Kepler tried before. So he was not basically, it's not like Peirce thought that he cooked up this ellipse and then he just tried it. No, he tried epicyclical models before, right? But he tried them in the heliocentric frame. Yeah, so I'll talk about this later. And yeah, how close depends really on the specific epicyclical model that you have. Yeah. So what I show here, that's a very simple one, right? It has only one big circle, the deferent, and one epicycle. Yes.
So if you're saying that Kepler worked in the heliocentric model, could he compare his model to the geocentric one?
Yeah.
So he would do computations that would
so he certainly,
that's pretty impressive.
So Kepler was trained in the geocentric framework because he was working for Tycho Brahe.
Mm-hmm.
Yeah. So he was basically a postdoc at Brahe's observatory in Uraniborg, and there he was tasked with coming up orbital theory for Mars. It's one of the sub-projects that Brahe had, and he had to use Brahe's theory, and that was a geo-heliocentric model, so it's a bit more complicated than what I've shown you here, but essentially the main frame of reference there is geocentric. So Kepler definitely could do these calculations, and they knew how to switch to transform the coordinates. But I don't think that they it's historically, I think, a bit unclear if they associated like any physical reality to that. So if they thought there was one better system or so. For Kepler, yes, but for Brahe, I'm not so sure. And I mean, the further you go back to antiquity, the less clear it becomes. Okay, so these are the models basically that I'll be comparing here, like a very simple epicyclical model, basically this one here, and the elliptical model. And to show you maybe in a bit more detail why people might think these epicyclical models are actually good, right? So I have here a picture somebody took with a smartphone of a basically a mass observation over the course of half a year or so. And I'm not sure, has any one of you ever observed like a planet like doing, okay. So if you go out like every other night and take a picture with your smartphone, or you look at the with your eyes, you can see that Mars makes this kind of what's called retrograde motion, right? At least sometimes, not all the times. So it really it switches its direction, it goes backwards and it switches again, and then it continues. And while that happens, it also changes its apparent size, like its magnitude. And in this picture, there's already one data reduction that has been done. Do you know what it is? No? So, I mean, Earth is like a moving observatory, right? It moves around the sun, but it also turns around. So you need to get rid of this, at least this turning around itself motion. And to do this basically, and that's how ancient astronomers have done it, by referring your coordinates to the fixed stars. At least, I mean, they're not truly fixed, but for these planetary observations, that's okay. So you basically, in this picture, it has been just, so you point your smartphone at the sky, you take the picture, the next day you do it again. You might do it at a different time, it will be in a different direction. But then you just overlay the pictures according to the stars you see in the background. Yeah? And that's basically what ancient astronomers have figured out very early, that you can do that. And with this, you get rid of one motion already. So this is not like something you would truly observe, right? So because if you sit down in a chair and you wait the whole night, of course you will have the overlaid motion. Mars is rising and setting again, like the sun. Okay, so already one data reduction involved here in this picture, but the epicyclical model has now So I just want to point out that there are like these loops that Mars makes. If you draw them, already Babylonian astronomers gave special points on them, some names, and the one in the middle, basically the top of this circle there, that's interesting for us. That's called the opposition point, right? This is important for the observations that Kepler then later uses to do his model selection. Now, the epicyclical model, in a sense, directly reproduces this retrograde motion, right? So even with our very simple model, which just has the deferent and the epicycle, if you let them rotate, this dashed line here shows you how the orbit then would look like, and you see it. You get these kind of circles and the backward motion in there. Okay, so far so good. That is why, or one of the reasons why ancient astronomers have stuck with this model for so long. The question is, can we now, I mean, if we put ourselves into this counterfactual situation, right, that we have this epicyclical model and then we have this ellipse, could we somehow directly choose them from the observations we make? Yeah. And of course, they are in different coordinate systems. Yeah, the observations are always in this geocentric coordinates. Yeah, we observe them from Earth, while our elliptical model, Kepler's model, that's heliocentric. So we would have to do something with the observations to do the fit in the first place. For the epicyclical model, we perhaps could do that more directly. Of course, this is something that we all noted that's already problematic for this very simplistic account of Mill. Namely, to do the coordinate transformation, you probably need some kind of background assumption, some theory. Yeah, and yeah, so it's not that easy. Yeah. So we can ask ourselves now, if we do this, if we somehow do this coordinate transformation, can we then at least do this model selection? Yeah? Can we somehow, with our observations, distinguish between the epicyclical model and Kepler's ellipse? And I mean, you could think, well, we just do the fit in the respective coordinate systems and then compare the error terms, the residuals. Basically, what our fit tells us the coordinate should be and what our actual observation was. And then we do it according to the which has the smallest discrepancy. Of course, it's also not that easy because you really have to factor in the error you make while you're doing your observations, right? I mean, your observations are not perfect. That was clear to ancient astronomers. It's clear to I think everyone. But it's something that Whewell, for example, completely ignored. He just thought it could be done. To give you an idea what kind of errors are involved in such an observation, I have here this famous quote from the Astronomia Nova by Kepler, where he says, well, we have this very good observer, Tycho Brahe, and he has observations that are so good that at the level of 8 minutes of arc, we can reject the epicyclical model. Yeah. So we were sure that the observations of Brahe were better than this 8 minutes of arc. Just to give you an idea, so these in astronomy you always measure angles, right? You basically measure two angles. One is the angle around you, and one is the one that points somehow up. Depends on your coordinate system. They tend to get different names. I'm not going to confuse you with that. But angle, the basic measurement is degree. That's normally used. And then you get like these smaller, if you go like a scale smaller, it's a arc minute, and then it's arc second. So arc seconds we won't talk about here in any case, because in ancient astronomy, people couldn't do observations at that level. But they could do observations at like the resolution of the human eye, which is about 1 to 2 arc minutes. Yeah. To give you an idea, so if you have your little finger, that's called the pinky, right? Mm-hmm. So if you hold it like this, then this is 1 degree. So a 60th part of that's 1 arc minute. And the width of the moon, if you observe it in the night sky or the sun, it's about half a degree. So that's pretty large.
So that will be 30 minutes, is that right?
Yeah.
Yeah.
Exactly.
So you can cover this with your finger.
Yeah, I can try.
Which is very, it's very amazing. It looks so large, but
of course that's I mean very approximate, right? It depends how long you're. And anyhow, so just to give you an idea what kind of accuracy these people were able to achieve, and for one reason or another, it's historically actually not quite clear to me. Kepler believed that this observational data he got from Tycho Brahe, they were accurate to about 5 minutes of arc, and he then saw that the fit he did with this epicyclical model that had a residual of 8 minutes of arc, so it had some kind of unaccounted for excess error, right? An error that was not accounted for by the observations.
These are still small differences, right?
Yeah,
it's very the point you want to make, right? So that it's astonishing how Kepler could be so confident.
Yeah. So was there some other question? Okay. Yeah, just to give you an idea what the instruments involved in such observations were. So what you see here, this is called a quadrant, right? It's a quarter of a circle, and that's the instrument that people use to basically since Ptolemy or even earlier used to get these angle readings. So it has this actually a painting from a book of Ra, which where he describes all his instruments. Yeah, and he has lots of different instruments like that. But this was the biggest one. It's called the Great Quadrant. Bit unclear how big it really was, but people say like the radius of this circle was 2 meters. Yeah, and you would have like a scale going around like horizontally. Yeah, that would give you one angle, and the scale that you can see here that's directly attached to the segment of the circle, that would basically give you the altitude of the star or the planet you are looking at. And then you would just there's this plumbing line here. I'm not sure if you can see that. So you would read from this plumbing line where it's on the scale. And yeah, this is actually me last week doing an observation with such an instrument, and I was in St. Louis and I visited the historian who did a reconstruction of this instrument. And this is not completely to scale, but yeah, you see from my head that it's actually also quite large. So it would not have been as accurate as the instrument that Tycho was using. Yeah, why did they build them so big? Because you can get more points on the scale, right? The bigger you make it, and this was basically their way to increase accuracy. Yeah. So in a sense, yeah, very very simple instruments. But we know now from comparison. So Tycho made like a star catalog. He has like 1,500 stars in there, like positions. And we can compare that to our modern observation, so we see how exact that is. And for most stars, it's like 1 to 2 Arcminutes. That's a really good. Okay, so just because Humphreys talked about this worry that Kepler would overfit his model, right? Kepler actually did only try one epicyclical model, and it was a very simple one. This one that you see here, like the one in the one of the earlier slides I showed you, it consists only of a circle, a deferent, and an epicycle. He called that the vicarious hypothesis, the helping hypothesis, because after he finished using it, he basically realized it was not correct. He selected the ellipse, but this was yes.
Like, why did he not try to make a better one, right?
Yeah.
Because you said for thousands of years they made better and better.
Yeah.
I mean, he knew all of that, right? So he could have followed that line. Why did he change track?
I mean, that's a very interesting question, but I think, and at the end, that's my something I'll try to argue. Something that diffuses this worry in philosophy, but that people would just go on and needlessly overfit, right? So Kepler specifically didn't add epicycles to get new and perhaps better fitting epicyclical models. And he stuck with this, and then he rejected this. But
it's not known why. He didn't say why.
Yeah, I mean, I will talk a bit later about his background assumptions.
Yeah.
He had like a physical theory, which somehow guided his thinking, but he also had like what we now would say are strong metaphysical convictions. And I think it's like an interplay between these two things. Yeah. But I'll say more about that later.
Sorry.
But, yeah.
I suppose the C is the center of the circle. S and E, what are?
Yeah, okay. So yeah, sorry. This picture is a bit confusing, right? Because it shows you the geometrical construction that Kepler uses, and in these geometrical constructions, you have always these kind of triangles and these angles that are then called anomalies. Yeah. So anomaly because they show that something differs from a perfect circle, so it's an anomaly. But what you have here is basically this is the circular orbit of the object that you're interested in. C is the center of that circular orbit, But to make the times, the motion needs to be constant around the center, but it cannot be the center in C. So it's actually the motion is constant around the center in S, which is the center of the deferent. And this is why it's a dashed, but the actual model is the dashed lines, right? But yeah. So these geometrical constructions, we can do this nowadays more easily in algebraic formula, but yeah, this is actually taken from a reconstruction of a picture that is in the Astronomia Nova. Yeah. Okay. So now maybe the most sophisticated treatment from philosophy of science so far is Sparno's argument, where he says, yeah, it's actually possible to do statistical model checking. A bit ahistorical, right? It's not a mathematical technique that was available to Kepler, but what perhaps we could imagine now is that we model the observational error statistically. So we say, maybe, okay, these observations are probably Gaussian distributed according to a Gaussian distribution. And we put this in our model specification. Yeah, so this is what Sparnos wants us to do. Then we run a linear regression on this epicyclical model, this vicarious hypothesis. I've shown you like this very simple two circles, and we do the same with the ellipse. And then we can check not only the goodness of fit. Goodness of fit is nice, says Sparnos, but actually what we should do is we should check the statistical validity, right? So we should check if the residuals of these models they show some correlations. And if we don't see any correlations, then our assumption. Yes.
Well, I was just going to ask, when you're doing this model checking, is there some amount of taking into account the like degrees of freedom of the model? Because I believe the epicyclic model would have more degrees of freedom than B.
Yeah.
Closer.
I mean, of course, there are statistical ways where you can do that, right? Yeah. So basically, these information criteria do just that. They have some penalty term for the complexity of a model. But that's not what Sparnos did in his paper. So what he did is basically he ran two linear regressions, one for the ellipse and one for this vicarious hypothesis, and then he only looks at their residuals. And he argues that if we can show that for one of these residuals we see correlations and for the other we don't, then we can accept or reject the model according to for which we see the correlations. Yeah, I'll just show you the picture. Then it's easier to see. So this is from his paper. Here this one is the epicyclical fit, and on the other side is the ellipse. Yeah, he argues then that for the elliptical fit, you see that there are strong correlations in there, right? So it's plotted on the x-axis, the observation order, basically the order at which you make the observation, the days here, right? And the same for the ellipse. And he in his paper he also runs some formal model checks, so you can do that in a formally specified way, like a statistical hypothesis test. But he also says that you can already see from these graphs that there's a correlation in the epicyclical fit, and the ellipse, he argues, looks more like a random process. Do you have any other observations of these residuals?
I see nothing when I compare these two diagrams.
Okay.
But I don't know much about
when I read his paper, the first thing that stuck out to me was that this one here has much more observations than that one there, right?
Mhm.
That's
Right.
strange.
Mhm.
And so what Spanos says is that he fit the ellipses on Kepler's original data, from the Astronomia Nova. And I'll show you later what I think is the table he took it from, because there are 28 values in there. So it's 28 days he does the fit. And he says he fits the epicycles on observational data he has from the, I think, US Naval Academy or something like that. But it's a much longer time series. It's like 2 years of data. And that's already strange. So this made me look, this actually made me look into this a bit more.
So the 28 points are over a year, or?
It's we can check in Kepler's table, and they're over more than 1 year.
Okay.
Yeah, they're very special points. So one problem with this is that he uses 2 different data sets to compare these fits, which I think is already from the outset perhaps not a good idea. The observational data from Kepler, I will talk a bit about that later. There are some very subtle points one can make there, but I think the more important point is that the epicycles are not fit on observational data. So I think what he did is, at least I tried to go to the website of this naval observatory, and they have a service where you can basically get you can generate yourself a huge table with the orbital parameters of Mars for any date you want, and that's an ephemeris. So it's ephemeris is basically a way of fitting observations so that you can predict positions of planets or stars or asteroids. So there are lots of ephemeris calculations online. NASA, of course, does them a lot, but these are not purely observational data, right? They are fit to observational data, but then you get an interpolating function. So what Spanos did here is he fit his model to an interpolating function between observations. Also, what one should notice is that the epicyclical model he fit in geocentric coordinates. He didn't. For that he directly took from this ephemeris the right ascension, which is basically the altitude of the star in the sky or the planet, and the distance. But the distance it's nice. It's in this ephemeris data, but it's not something that would be available to Kepler. Kepler didn't have any good distance measurements of Mars. So that's already something one could be critical about. If one looks at it, maybe one could have the idea that one could basically try to do his statistical model check the other way around, right? So we could try to take the ellipses fitted on the ephemeris data, could take the epicyclical model and fit it to Kepler's observational data. And I actually have done that, but before going there, I'll briefly say something about this supposedly original observational data from Kepler. I've taken this table here, which has 28 values, and I think it's exactly that because I reproduced the fit, and it looks exactly like the one in Spanos' paper. That's the one that he took. So this is from chapter 53 in the Astronomia Nova. It's from Donahue's translation. So this is why it's all in English, right? And in the original it would be in Latin. And you see here these columns. So for us, important is the Sun-Mars distance, the mass eccentric position on the ellipse, and these two here, the computed and the observed position. So Kepler here gives the impression that he compares a fitted model with observations. And because there are these Sun-Mars distances. So what you could think here he does is he has the elliptical model. Yeah, here's the Sun in one focus, and then he has Mars at some points, and the eccentric position on the ellipses like this. So this one column there, it's just this angle here, right? So between two positions of Mars and ellipses. So this is something that he could have observed. The Sun-Mars distance, that's not so clear. Wait, got that wrong. I mean, he had a way to get at these distances, but not for all these 28 points here. And the translator already noted, because he recalculated these tables, that there's something odd here. And he argues also in the paper that these Sun-Mars distances and also actually the positions here, they are not observations. He argues that they have been calculated by Kepler retrospectively. So what Kepler has basically done, he says, is he has fudged these data so that already assuming the elliptical orbit, this is the distance and the positions you would get out, right? So it's like yeah. So certainly these are not empirical values you would naively fit your model on if you try to make this kind of argument Spanos was trying to make. Okay. Just to quickly go through with that, what I've done here is I have just taken ephemeris data and fit an elliptical model to that, and you see residuals get these kind of you see actually correlations in there, right? And it's also no surprise that you see these correlations. Why? Because we know that there are orbital perturbations. Yeah, and I think what we see here is actually the orbital perturbation that Earth does on Mars's orbit. Yeah, reflected in the ephemeris, because these ephemeris, they are very accurate. So because we have spacecraft we send spacecraft to Mars, we know the orbit of Mars with an accuracy for about 10 meters. Yeah? So we see all this in our fit. So we shouldn't actually expect this statistical test of Spanos to go through in any case if we use ephemeris data. Yeah. What we can then do is we can do the same with the epicycles. Here I have instead of using these so-called observations from Kepler, I have used ephemeris data but introduced a Gaussian noise term to them. So I have artificially wobbled them around, and I have the standard deviation is like the observational error that Kepler was working with, like these 5 degrees of arc. So you can see here it looks like super random, right? So this looks much more like a random process. So I would say with this Spanos idea, as nice as it might be, you cannot really do it with the historical data. Yeah. So with the historical data, you cannot statistically distinguish even between the vicarious hypothesis, which is a very simple epicyclical model, and then the elliptical model on statistical grounds alone. So it might be possible if you take much more data. Yeah.
How much? How much more?
Oh, I haven't tried that, but I think yeah. So at least at least 2 magnitudes, right? And 2 magnitudes of the order of data that Kepler had. And if we are honest, then Kepler did his fit on 4 data points. Yeah, he had 4 positions of mass, which he then used to calculate everything else. So, yeah.
So the data you showed us on the slide before, is that all Kepler had, or
No, Kepler had some more observations, but because he needed to transform everything in the heat, so these are all geocentric observations that Kepler had, right? So he needed to transform them into the heliocentric frame, and for that you need the distance between the Sun and Earth and Mars.
I see.
Yeah.
So the numbers you said he could not have observed, but he needed them to make the transformation.
Yes.
Maybe I'm misremembering my history, but didn't Kepler have his orbital laws before the ellipse?
Very good.
And couldn't those better describe an ellipse than they would happily? I mean, I don't know how well they describe an elliptical.
So you're spoilering already a bit. But this played, in fact, a huge role. So Kepler's, what is now called Kepler's second law, that in the end was, I think, what somehow convinced him that the ellipse is the correct orbit. Yeah, I'll say a bit more about this later. But yeah, so maybe saying one more point about this coordinate transformation. So there are these opposition points I showed you before, and in these opposition points, basically Mars and the Earth and Sun, they are in one direct line, and this is what Kepler used to get the distances. Yeah, but these oppositions, I think he had a couple of more than 4 of them, but in the end he used 4 to get the distances.
Mm-hmm.
Yeah, so
it's crazy.
Yeah, that's and I mean there are lots of other steps involved too, which I just ignored here. Basically, what he did is not to directly get the orbit of Mars, but he used these points to estimate the orbit of Earth. And then he refined the vicarious hypothesis for the orbit of Earth, and then he used that to transform the other coordinates. But yeah, you see, it's a very, already at that time, a very complicated data reduction.
Mm-hmm.
Yeah.
So the idea is that he had the Tycho data, but he could reduce Tycho data only a small part of Tycho data.
Yeah. So he had these very special observations, right? Which the opposition observation. So and it was already known to astronomers that this is an opposition. So they knew when these things happened, and then they observed them. And I think he used 4 of these Mars oppositions from Tycho's data, and with that he got a better approximating theory for the Earth orbit. And once you knew the Earth orbit to a certain accuracy, he could transform all the other observations into heliocentric coordinates. Okay. Yeah. So yeah. But it really hinges on these 4 observations, right? Okay. So I think, I mean, it's a nice idea by Spanos, but if you use the historical data, what was available to Kepler, you cannot really argue that you can distinguish these 2 models. Yeah.
Mm-hmm.
So it's just speaking from the data, I think it's impossible. And that brings us maybe back to Humphrey's worries with this idea, not only that Kepler would be fitting the simple epicyclical model, but basically that he had the possibility to add epicycle upon epicycle, right? And as you might know, there's now like this whole cottage industry. It's often rediscovered that you can basically trace any complex curve with epicycles. And this is pi, but there's also the Homer Simpson orbit and other things. Just Google it, you will find it. And And of course, there's some kind of a mathematical approximation theorem in the background here, right?
It's Fourier.
Yeah, exactly. So it's just a Fourier transform.
Can I tell a story?
Yeah.
10 years ago, more, no, 15, 20 possibly. We wrote a paper with Daniele and other about philosophy of data science, where we argued that there is a sort of that data analysis realized a sort of explanation without understanding. And Humphrey was one of the referees.
Oh.
The argument of Humphrey, that because then the referee was published apart, it was exactly that we do not have argument that there was not an epicyclic system that worked behind it. This was exactly his argument. So what is the difference between your agnostic science and the episystic system? Epicyclic system. So when the argument was when you use enough you can adapt any data.
Exactly.
That's exactly the argument.
Is this related to the approximation theorems you mentioned over lunch?
Yeah, I mean, this is
again the same thing.
Approximation theorem that I had in mind there, not the Fourier one, but
yeah. Okay.
Yeah, but of course, I mean, so I mean, this was Humphrey's worry, right? And also, I interestingly, he never thought about this in terms of Fourier analysis. So I talked to him about this, and he referred me to there's a paper by Hansen. It's about the mathematical power of epicyclical astronomy, where he basically rederives this Fourier approximation theorem, but he doesn't somehow notice it. It's a Fourier approximation theorem. Anyhow, yeah.
I think he didn't watch the 3 blue, 1 brown videos because like he has a very nice and then you see it immediately because it's just the same picture.
Yeah. But of course, one also has to say that ancient astronomers, they really didn't. It's a bit a caricature, right? They didn't add epicycle upon epicycle, right? It's not. They tried to do these very simple epicyclical models.
So how many epicycles did they add?
It's actually hard to count, right? Because I mean, I've been thinking about this. If you the best way to do this would be to find the equivalent Fourier series representation and then just count the terms in there. But they have all these shifted things, right? So they shift the circle a bit to the right.
I see.
And then they add like a small circle here. So it's not very systematic. And then people, I mean, there have been huge historical controversies which epicyclical model has more epicycles.
Okay.
But they tended to be all very simple, and these numbers you normally read in like these popular science accounts where they say, well, they had like, I don't know, 28 or 34, and in the medieval times they increased that to 100 something. This is because you need an epicycle for, of course, every orbit. But I mean, this is also not fair to compare to the elliptical model because, I mean, you have a different ellipse for every orbit too, right? Different orbital parameters. So, yeah. Okay. So just for the fun of it, I fitted also like a very low order Fourier series on these so-called observational data from Kepler, just to see if you could statistically distinguish them, right? And what you see is the at least to me, I don't see any obvious correlations here in the residuals of this Fourier series. So actually, maybe this would have increased Humphrey's worry, right? Because you cannot even statistically prevent someone who really wants to add epicycles to do it. Yeah. I mean, we already have talked a bit about that. Could Kepler have tried more epicycles? For historical fact, he only tried this very simple one, and then he stopped doing epicycles. But there's some historical evidence that he could have put some more, right? So he maybe could have gotten to 5 or so, according to the power of his mathematical methods. So there are people, historians, who have argued that that would have been possible, and there are contemporaries who have actually done more complicated models. But of course, at some point, the computing power or his patience would have run out, and he couldn't have done the fit anymore. And then you get into the Humphreys model lock-in scenario, where you basically your computing power dictates which kind of subclass you can explore. And if you get a good enough fit within that subclass, you are stuck to that, and you will never find the correct model. Yeah. So the question now, what did Kepler actually do? So I hope it has become clear so far that he didn't directly fit the ellipse, as many philosophers have thought, and perhaps many textbooks have claimed. So what he did is that he noted that there were discrepancies between the epicyclical model, the vicarious hypothesis, and the observations. Yeah, and he noted that there was maybe 3 arc minutes that were unaccounted for by observational error. Yeah, so this is already a more complicated situation than many philosophers have imagined. But what he did then was he tried to tinker with this vicarious hypothesis. He tried to introduce some eccentricities, try to obtain better fit. So really, perhaps what Humphreys would have warned against, but he didn't add any epicycle to that hypothesis. But it didn't work, right? So he tried a lot, and he documented his struggle in the Astronomia Nova, and at some point he just gave up. And he rejected circular orbits. Yeah. So this is what he could do with the empirical observations he had at hand. And then comes his physical theory. What he then did, he didn't directly say, I'll try an ellipse. He thought it would be more like an egg-shaped orbit. Yeah? It's called ovoid shape. Yeah, so that's what that's the next model he tried. And this ovoid actually presented computational problems to him. Yeah, he couldn't do the integration of it. He couldn't calculate the areas between two points on this orbit. So it was, in a sense, it was mathematically intractable to Kepler, right?
What is an ovoid, mathematically speaking?
Yeah, this is an ovoid, for example.
Yes, but this is so the shape. Mathematically.
So there are, of course, different formulas for ovoids. There's not a unique formula. I didn't put Kepler's construction here because it's very confusing, but he had a geometrical construction for that. So he had a sometimes called the puffy cheek orbit, okay, because it looks a bit like somebody with puffy cheeks. Yeah. So he tried to fit that, but he really struggled with doing that, and in the end he also figured out that it was not supported by data. And then the next best thing he came up with was the ellipse. Yeah, the ellipse had the upshot of being mathematically tractable. Yeah, so with his geometrical methods, he could actually do that, although it was not really empirically distinguishable from these other ovoid shapes that might have worked too. Yeah, but he just used that in the first place as an approximation to an ovoid. Yeah, he says that's something in between a circle and an ovoid. So the easiest shape that I can calculate with the ellipse. So there's this interesting quote of Newton in a letter to Halley, who says Kepler knew the orb to be not circular but oval, and guessed it to be elliptical. So maybe Peirce was right after all, right? He really guessed the ellipse. But later, or the ovoid shape itself was already selected on, I would say, theoretical grounds. Yeah, so he didn't have convincing empirical data for the ovoid shape either. He just knew it's not a circle, the orbit, right? And I'll say a few words about this theoretical convictions that Kepler has. So this is normally called Kepler's physical theory, but nowadays we wouldn't call that a physical theory. It's not really mathematized, yeah. So it has this idea that the sun is the prime mover in the complete cosmos and that it controls all the movements of all the other objects in space. And he actually had some kind of rudiment of a force law for that sun. But this was wrong because he modeled it after some kind of magnetic force. Or what people at that time knew about magnetism. Yeah. So he read a tract by a physicist called Gilbert, and he was writing about magnetism. And the force law basically that Kepler then came up with is a linear force law. But this linear force law, even though we now know it's wrong, it led him what we now consider Kepler's second law. But at that time, he didn't ever call it second law or anything like that, right? So it's this equal areas, equal times law. And this is in the end what made him accept that the ellipse is actually the correct model, yeah? Or what biased him was towards selecting this ellipse. So it was more like these theoretical, perhaps we would now say metaphysical considerations that led to the force, the second law, the force law, and through this force law to the second law, and then to this model selection. So it was not completely determined by the data. Yeah, so I just have this here because I want to show you that not everyone was convinced by Kepler's physical theory. That actually in the astronomers and physicists after him, they haven't accepted it, right? So Mestlin, he was a teacher of Kepler. He wrote to him in a letter in much after the Astronomia Nova was published in 1616, basically saying that he doesn't believe in Kepler's physical theory and that the physical causes Kepler makes out should be operational in the heavens. Okay, so just to wrap these things up, I think the three important aspects in Kepler's model selection were that he accounted for observational error, but of course observational error meant that there was empirical indistinguishability, right? So you still have this kind of underdetermination by observation of your models. Then tractability certainly played a reason. Yeah, we saw that he first picked the ellipse because it was an approximation he could mathematically handle. So it's the computing power aspect. But there was also background knowledge. Yeah, his ideas about the sun and how the sun mediates the force and controls the movement of the planets. And this was certainly not saturated by data at all. Now back to Humphreys with this observations in mind. Could Kepler have overfitted this epicyclical model? I think in the historical context, this seems increasingly unlikely. Yeah. So while we could have probably forced him to do it, yeah, at least a couple of more epicycles, he had some strong reasons not to do it. So he didn't select any flexible model he could have selected, and his model class was actually constrained by the observations and the observational error. So this is what perhaps Mill, Buell, and Spanos got somewhat right. The computing power. This is what Humphreys got right, the background knowledge. So I have a question mark here. I'm not sure any philosopher talked about this, but I should say that this has been analyzed in the history of science a lot. So the historians certainly knew about all these things.
Kuhn argued about that, Coiré.
Yeah. Coiré, Coiré.
No?
He doesn't say so much about background knowledge. He is also a very simplistic.
Yes, by the idea there is a Platonistic
Yeah.
conception where that, and the Kepler is influenced by Plato metaphysics. Kepler constructed
Yeah.
Kepler, Coiré
Yeah.
constructing that and industry about that.
Yeah.
Now I don't remember exactly
Yeah.
where I
There's
speak
a very-
about background knowledge, but it seemed to me,
Yeah.
but I can be wrong. I read it.
Yeah. So I get, but so for me, Poiré is a bit also more of a historian.
Yeah, no, that is
Yeah.
true. That is true. And Kuhn should have
Yeah.
do that in the Copernican revolution.
Yeah. So Kuhn certainly says something about background knowledge. So
Yeah.
maybe
Yeah.
that's the one I'm missing here. But there also, of course, I think there was some kind of luck involved. Maybe this is a kind of vindication for Peirce, although it's not merely luck, right? So not like this abduction process that Peirce imagined, where you guess something and then you check with the data, and if it's not right, you guess something new, and so on. So yeah.
The last factor is the most important.
The luck factor.
The last one.
Mhm.
Luck.
Luck, yes.
Okay, let's go.
Okay, so I think to get a big transfer this Kepler example, yeah, which was a historical example, more a bit maybe about our contemporary worries about overfitting. And I think this is what Humphreys was getting at, right? So Humphreys was not really worried about Kepler, as he just used it as some kind of illustration. He was worried that with modern computing power, he would be in a similar situation, that basically it unlocks new model classes which have nothing to do with reality. So we have this increase in flexibility and the increase in computing power. But I do think this does not make overfitting necessarily more likely, because what this Kepler example shows us that there are always lots of other factors involved too, right? It's not only this flexible model and computing power, it's this background knowledge and some kind of contingent factors in history. And I think we should only be worried if we ignore all these factors, or perhaps put us in a situation where we ignore all these factors. Yeah. So of course we can say I don't want to make any kind of background assumptions. I don't want to do anything. I'll just use this model, which is very flexible. There's an approximation theorem, and then I throw as much computing power at it as I can to fit something. I mean, we can do this, but I'm not sure if anyone does it like that, in that very direct way. But also don't think we should do that. Okay, and that's already the conclusion slide. Just for my own field of philosophy of science, I think need to be a bit more careful with these historical illustrations. So the context of discovery, I think, is really not just a given. If you look at the work historians have put in teasing out all these aspects of the discovery, of Kepler's discovery, that is something that I think should be reflected in philosophy too. So maybe we need to tune our examples a bit, and it should be a bit more or true to how history actually worked. And of course, I think what we also see in this Kepler case, that hindsight is a strong bias, right? There's a strong bias on the illustrations we are apt to use, and the things we are want to forget. Yeah, just as a take home, I think many factors play a role in model selection, and philosophy of science has put in like only a flashlight on some of them. Yeah.
So I have a question.
Yeah.
If the director of the computer science center that you work had listened it, he would have fired you? I mean, no. I joke, of course. My point is that in some sense, you're arguing here that the powerfulness of the computation, the tools that the computer give us to us, is by far not enough to make a real scientific progress happen.
I think.
And so this is true for Kepler, but is also true now.
Yeah, I think we'll say that. But I think also my director would agree.
No, that's not a joke. Do not take it seriously. I do not want to fire you.
That's why you got your job in the first place, right?
I cannot joke. It is word. No, my point is that you think that the lesson of Kepler is also a lesson for us.
Oh, yeah.
But nowadays, we receive so much information from all the telescopes and everything, and then we just have servers, plenty of data that is waiting for us to analyze, and the computer power is limiting us to obtain all the information that this data that is available already.
Yes, no, but of course. So I do not understand what you want to mean. So of course, now the question of the orbit of planets, in some sense, the data is only there to see, to compare with an hypothesis and a theory that is there rather than to fix another one. So perhaps the example that we should consider now is not the orbit of planet, but other orbit. But the point is whether this story can, in some sense, respond to the way in which a computer today act in the development of science. That is, that the data is not enough. Or to do it in other sense, what is the role of computing? So what's your point? I do not understand your point.
I thought that you were asking whether the computing power is still not enough to solve some of the problems that we are asking, and the answer is yes. The computing power is a limiting factor.
It's a limiting factor.
It's a limiting factor. Yes.
Why?
So because we have lots and lots and lots of data. Because we can observe the sky, and now we can take pictures, and we can in different frequencies and everything, and we have all this data there, and it needs to be analyzed, but it is so much.
Can I actually jump in here?
Yeah,
so I actually have kind of a different sense. So I thought one of the things this talk might cover is this idea of double descent. Have you heard about the bias variance trade-off and double descent? So it always used to be the case that, you throw more compute at the data and you face this bias variance trade-off, right? You fit this data better and better, but then you do wildly bad out of sample. You end up overfitting, right? But with this new computing paradigm with neural nets, et cetera, we've hit double descent. You just keep on throwing more and more data, more and more compute at the same data, and eventually you start stop overfitting. You get this really great extrapolating out thing. And as a matter of fact, these large language models are actually over-parameterized. We have lots and lots of data in them, but we have even more enormously more compute in them. So I think that makes you should be more optimistic. So I'm not disagreeing with the point that more compute would help, but the reason that we need more compute isn't that because we have too much data to analyze. We got to over-parameterize it even more.
I think I kind of disagree with a nuance there.
Okay.
Because if you think about what Kepler was doing, and if you took all the points and just threw them into some neural network, you'd get something that fits it very well. but you'd be still like missing like the concept of the ellipse, like the
Yeah.
simple solution. So
Maybe. I mean, but that's what they're trying to do right now. Right now, these big companies are setting up like play physics systems where, agents can run around in them and try to learn physics from the play system. Now, maybe that's simulating a Kepler, and then, you still need a Kepler in there, but
I guess it comes down to like, what does it mean to like know science? Like, is just having a neural network that will just tell you what's going to happen next, is that enough to like have solved things, or do we need to know more, like an intuition to know why?
right. Obviously, I think they are different things. Just because you perfectly predict a thing doesn't mean you have a theory of the thing necessarily, or a very good theory. I actually had a slightly different question. Hopefully this isn't too much of a digression. The magnet example, I mean, it seems pretty obvious if you just play with a pair of magnets that there's not a linear force, right? They're way stickier, closer together. Is Newton the inventor of inverse square laws? Was that just completely outside of people's knowledge?
Yeah, so it happened with Newton, I would say, yeah. I mean, there certainly were predecessors, but yeah, people tried lots of different things for both laws. But I think with Newton, you really, for the first time, you had like a consistent, complete theoretical framework, yeah, where these Kepler laws would fall out. Yeah. This I think was very, very important for Newton, that he could reproduce these laws.
Yeah, I mean, I don't know if this is what you wanted to like talk about, but if we're looking at these sort of sense of what these models are here, they're kind of like a simple in the sense of a mathematical object. They're just a function from time to like a
Yeah.
But in modern physics stuff, I'm not entirely sure how, like, what types of objects are models, and can we like compare them? Is that kind of figured out in a way?
You mean what philosophers think are models in modern physics? Yeah, for example, the Ising model is always, this is like the modern Kepler. It's the model everyone talks about. Do you know it? The Ising model? Yeah, it's a spin model, was invented in the 1920s. It basically arranges little magnets in a grid, right? And then you have like a so they can only point up and down. So maybe I should do a square lattice here. And what you can do then is you have a next neighbor introduction or interaction. You write down the Hamilton function of the system, then you calculate your thermodynamical quantities. This is a model.
Does it parameterize like a space of models the same way like a function that like maps a planet? You could have all different.
Yeah. So what you mean? What are the? Yeah, I mean here you have like it's a discrete model, right?
Yeah.
So you have a degree of freedom in the spin, and then you have the index of basically it's a matrix, right? So you have a double index for this element. The functions you get out of there are different, so you can get like all the things you get from statistical thermodynamics. Like the can calculate temperatures.
But it is like a correct model varying by like initial conditions, sort of, opposed to like when we're talking about the models of orbits, there are ones that are like not correct, and we can kind of compare.
This model is clearly not correct for magnetism, right? And it was it's a toy model, yeah. But there are also more complicated versions of that which model other aspects of magnetism more realistically. I mean, the Ising model, it has lots of applications. I mean, it's not only it was invented in the context of magnetism, yeah. quantum mechanics and magnetism, but it's nowadays used. People have found out lots of applications for that. So I'm not sure if we then can say is it like a correct model or not. In a sense, all models are wrong, right? But some are certainly better than others. Yeah.
Go. I already asked.
So I wanted to ask whether there are some lessons for research on explainability in AI,
Yeah.
right? So, like, an AI model can be pretty much a black box, like just data, right? So a bit like Kepler was looking at data, and then we're trying to find some explanation, and kind of Kepler found the ellipse, which is a beautiful explanation. But as you emphasize, it's not just coming from the data, and it's not just coming from throwing more compute power at the data, right? So when we as humans are looking for a good explanation, we're looking kind of for more than just prediction, right? We're looking for more than just accuracy. And I feel like the literature on explainability in AI is very unphilosophical. It's very blind.
Oh, yes.
So just every paper, as good as it may be, it's just kind of basically discussing an example of what a good explanation could be.
Yeah.
And then because they focus on a particular example, I mean, the papers can be quite convincing, but they're actually not tackling the question that the title of the subject area seems to suggest, right? And so I was looking for, like, I don't know, are there philosophers of science who have something interesting to say? I mean, I know the old research in philosophy by Hempel, I think is one of the names, right? So, but that's completely not, it has nothing to say about explainability in AI, right? So we would need something else, right? And so I was just wondering whether you have some thoughts on this.
Yeah, so I actually have written a paper on that.
Oh, nice.
But my take on this is basically what these XAI methods do is they explain one complicated function with a simpler function, and they do this in a and the way they do this is depends on the author, right? So, but the authors always claim that what they do is like a good way or maybe the correct way of giving this explanation. But what one should note there is that there are lots of decisions involved in this, which are often made not explicit. So you only see them when you look at the actual implementations of the algorithms. You see what kind of decisions they perhaps maybe not even consciously made. How to reduce this space of the complicated function to a simple function, because it cannot be done in a unique way with preserving all the information that is in this larger space. So there is something that gets lost. It's actually the best analogy for that is map projections, right? You project from a three-dimensional space or a higher dimensional space to two dimensions. You always lose something. And then map makers they can face these trade-offs in a different way. But it's to me unclear how these producers of XAI methods face these trade-offs, because then they never like really talk about it.
Thanks. Yeah, that was interesting.
An historical question. You at a certain moment argued that Kepler used this to infer the first one.
Yes.
So it's not clear to me how this could work, because I don't understand the meaning of the second law without the first one. So what is the second law if you have not the first one? So what's your point? It's not clear to me.
I think that for that you have to really look into the details of how Kepler came up with this elliptical hypothesis, and he of course didn't formulate in the first place the second law in terms of an ellipse, right? So he had like this geometrical construction with circles for it. And I mean, if you're really interested in the details, there's a great paper by Bill Donahue and he has worked this out very clearly.
But if you have a circle,
Yeah.
so unless you think that the circular, the rectilinear, the velocity change on the orbit, if you have a circle, it is very strange to imagine, or the second law is obvious.
On the circle.
On a circle, the second law is obvious if the speed is constant.
Yeah, I think so. I mean,
so I do not understand also how you can state the second law on circle. It is trivial. The second law.
You can state the second law. When in an orbit, you could say that there is an orbit, has any shape.
Yeah.
And then the areas that are covered are equally is constant. That's it.
Yeah.
You don't need the orbit to be.
You need a position of.
You need the position of the observer, or the position of the sun, and the position of the planet
and the orbit.
That's it.
And then you can. Yes, but then how can you use it? Argue for the fact that the orbit is.
So, for example, imagine that you know that this. I don't know how Kepler did it, but imagine that you have this data. You know that the distance of the planet to the sun through the year, and then you say, okay, I'm going to draw a circle. I'm going to divide my circle in 360 days. I'm going to assume that my planet is traveling at a constant velocity on this circle, and then I'm going to plot the distances from the planet to the circle at every single point, right? The shape that you obtain is not an ellipse. Let me just. So you imagine that
there planet, is a mass.
Yeah, but it's not. Imagine that you have. You say, this is the sun, and this is a circle, and I'm going to divide this circle into 365 points.
Okay.
And I'm going to assume that my planet is traveling uniformly around this circle. So this is the first day, this is the second day, and so on. And then you also know the distances of your planet to the sun. And then you say, okay, the first day, my planet was here. The second day, my planet was here. The third day, my planet was here. If you do that, you do not obtain an ellipse.
No, certainly.
Because this velocity is uniform.
Yeah.
But if you have the second law and you have the distances, you obtain the ellipse. I don't know how Kepler.
Yeah. So I think it's important to note that Kepler didn't have these distances, right? So at least only
So you have the distance from the center any day, and you suppose that the speed on the circle is constant.
Then if you do that, then you don't have.
And you're sure you have the ellipse in that way?
You don't have an ellipse in that way.
No. If you have
if you assume that
the second law, you said the second law, you have an ellipse. So you change the speed.
You need to change the speed of the planet.
You change the circular speed.
Well, you
calculate. What you say that you calculate the circular speed here and here, the ratio between that under the condition that is
the areas have to be
in equal time.
Yeah, of course. Yeah.
Okay. And the third law, when how it appear the third law?
That's a good question. I haven't looked too much into that. Yeah. So I actually don't know.
Okay.
If Peter has a question.
Other questions?
I'm curious because, I mean, my understanding of this scientific revolution that was subsequent to this result is more, I've interpreted more as a validation of Occam's razor than the idea that it's just you have to measure accurately and let the data speak for itself. I mean, it's clear that Kepler did that, and that it took many years for him to be able to make a case that he's correct. But the ellipse is so much simpler than the epicyclic model that, and ellipses were known for millennia before that, geometrically speaking, and maybe.
But okay, why? So you argue that
it's the shift from the geocentric point of view to the heliocentric point of view that made this be so revolutionary, and the fact that he was able to show that this is validated by the measurements. So he's not just saying ellipse explains this, but if you want to explain it by just looking from the Earth position, which is what all human astronomers do, then the epicyclic model is a fair explanation, but the elliptic model is much simpler because it's just coming from a slightly deformed circle. The interesting thing is that the orbit of Mars is not even very elliptic, and it was from a heliocentric point of view, it can actually be quite well described as a circle, but from the Earth's point of view, it's clearly not observationally a circle when you look in the sky. So I don't really know why Mills, when he picked this example, thought that that was going to be such a strong case, because I always viewed it as something that is a strong case for picking what would be a very natural replacement for a complicated model, or something that is evidently a better model, whether it's the accuracy of the model or not. It's a simpler model to explain what's going on if you're able to do all these coordinate transformations. And that was the difficulty, right? That's, as you alluded, he didn't have all the data that was even needed to do this. So it's amazing that he was able to make a successful case. I'm actually curious, after that, how soon was it that other planetary orbits were observationally established as being ellipses around the sun?
Yeah, that's a good question. I don't know, actually. But so I think, so interestingly, there are some contemporaries of Kepler who didn't believe in the ellipse, right? So for example, Cassini, he tried with oval shapes.
So Kepler only gave the third law for Mars.
So in the Astronomia Nova, he only states that the Mars orbit is an ellipse. Yeah.
No, but I mean the third law is about this semi-axis of the.
Yeah. But so the problem with these laws is that Kepler never gave them a very prominent position, right, in his book. So if you look at this book and you would like to find some kind of section which says law number 2, you won't find that, right? So it's like somewhere hidden in the text, and only much later people came to attribute this significance to it.
But Kepler was convinced he has done something significant. So what would he think was the significant contribution if it was discovered in ellipses?
So I think first heliocentrism, so that he could do this in the heliocentric.
But Copernicus had.
Yeah, Copernicus, right? So he was not like the first one, but of course he had a better agreement with observations than Copernicus.
Yes.
Right, so he was okay.
Yeah, so he was empirically more adequate, I would say.
But would he consider himself as improving Copernicus? That was maybe his.
So I do not understand the question. What was the question?
No, because Nico said that Kepler didn't make a big thing out of having discovered that it ellipses, right? And then what was the big thing in Kepler's own thinking? That's the question.
Yeah, so I mean,
why you think that it's not fair? Why the Kepler law would not be a big thing?
I mean, I just took this from what Nico said.
The question is for you. In
which
sense they are not a big thing?
No, so So you asking what significance was Kepler attributing to himself, or what was the single most important? Yeah, so I think it actually was his physical theory that he considered most important.
So what we consider
what we basically have forgotten.
Yeah, that's very interesting, right? So how, that's very interesting.
I mean, I was wondering because to me, maybe it's not a priori evident that the ellipse is the simpler model. And I was thinking particularly from the perspective of like constructivity with like compasses and straight edges. Like in the analytic sense, an ellipse is pretty simple to describe, but with an epicycle is difficult. But with a compass and straight edge, I feel they're both.
That's a very good point.
And I was wondering how much like that affected people's perspective, like the more constructive opinion.
But the ellipse is very easy to construct with the Gardner system.
It's a conic section.
The Gardner compass constructing the ellipse easily.
Yeah, if you have the extra stuff to do it.
No,
like a rope.
Yeah.
with a rope.
Yeah.
The sum of the distance of the Fauci is the same. So with the Gardner system, you construct.
But maybe this is also related with part of the explanation. Maybe Kepler thought that his physics was more important than the other thing, because the physics is what is giving you the explanation, right? And Newton is the one who also gives physics to explain Kepler. So how do you explain that the planet is circling around a point that is nothing, right? So the point is orbiting the Earth or the Sun, but the planet is orbiting that point. What is that point physically?
I don't think he had a grasp of, I mean, like why it would be an ellipse as much as why it would be an epicycloid. And I do think that from a constructing drawing point of view, using a rope to draw an ellipse and using a circle around another circle to draw an epicycloid are relatively similar levels of complexity in my mind. So,
but maybe now we have an explanation. If we put this together with what Jose said, so the ellipse became the explanation after Newton.
Yeah.
Because Newton could explain the ellipse, and now the ellipse could explain Kepler. But Kepler didn't have Newton. So for him, the ellipse wasn't obvious. Wasn't obviously the contribution from it. Yeah. I like this a lot. This is showing.
It's not clear to me your point about the ellipse. The ellipse is a circle that you simply divide the point in two. Of the center of the circle, and then you take 2 points that are one. The center is you suppose that the center is made by 2 points superposed one to the other, and you divide the 2 points, and you have an ellipse. So the most obvious generalization of the ellipse is the most obvious generalization of the circle that you can imagine.
Well, I from like a construction Greek type point of view, I don't like both of them are going to require non-compass straight edge tools. And one, like the ellipse is very simple, I agree. But an epicycloid is just running a wheel along the surface of another wheel. It's just like a wheel turning and tracking the point.
No, but look, when you construct an epicycle, you simply do not construct a circle, because you have to construct a circle on a point that moves on a circle. That you want to make a machine that constructs the point that move on the epicycles. This machine is much more complicated than the compass.
Yeah. But
because you have to compose two circular motions, not a motion, a rectilinear and a circular. Not to compose. You can construct it, but you have a machine that is much more complicated than the Gardner construction of the ellipse.
Have you ever seen those like toys with like the gear and you like track it with your hand? Yeah, that's not very complicated. So.
Yeah, but we already see the problem we have with the Occam's razor, right? So it's like not the measure of complexity is just not very clearly defined here. And yeah, I would tend to your position and say that the ancient astronomers, they preferred the circles, maybe not in terms of simplicity, but because they thought circles were the most perfect objects.
Yes.
And everything that was deviating from a circle, and you already see that in the in the names they give of the quantities that deviate from a circle, like anomaly, right? Eccentricity.
And then the other side is not clear to me why the simplicity or no simplicity of the geometrical constructibility of the curves should be an argument about the trajectory of the planet. But the fact that the circle is perfect because of metaphysical perfection of the circle, the universe is perfect, so to be circular, I understand. But the fact that the circle is very easy to construct does not seem to me to be an argument for the fact that the planet should move in circle. So the fact that even if I would agree with you, which I do not agree, that constructing an ellipse is equally difficult, let's say, that constructing the orbit of a planet of an elliptic. I would not see why it should be a reason to favor the epicycle, the vicarious hypothesis on the elliptic one. Why the constructibility should come.
I mean, I don't necessarily believe it should, but from the perspective of historic physicists, I think they cared a lot about like the geometric perfectness of their theory.
Okay, I think that we could make a 5-minute break and then
Thanks again.